Faraday's law. So Lenz's law is really just telling you the direction of Faraday's law. But what was the key thing? What's changing? The magnetic flux, okay? And it's changing in terms of what? Like changing in space, area. Changing in area, changing in...
Yeah, the area.
In amount, I guess.
No, like if you take a derivative of the flux, what's the derivative with respect to? Time, okay? The flux has to change in time. So remember, like either the magnetic field's increasing or decreasing over time, or the area is increasing or decreasing over time, or the angle is changing over time, right? It's not instantaneously different. There's an amount of time that passes it. It's going to rotate at a particular rate or get bigger or smaller at a particular rate, okay? Which is why in the lab, when you move the magnets faster, you get bigger currents, okay? Because how fast you do it in time, how big the change in magnetic field is over the time is what dictates the current, okay? So how do we write that in math? Well, we have the EMF, which is the voltage, unfortunately. That's going to be negative magnetic flux over time, okay? And so this is sort of the simplest expression of Faraday's law. There's a little bit more to it than that, but in terms of what we're dealing with in Lenz's law, this is Faraday's law. And what does this negative sign mean? This is actually pretty important. So this is the part that says it opposes change. It's like when we have force equals negative kx, right? That's the restoring force. So when you stretch a spring this way, the force goes that way. So it opposes the change. Remember, Faraday's law and Lenz's law, the direction of the induced field opposes the change in flux. So this is how we indicate that. So the direction of the voltage that's generated, and therefore the current, because how do we get from voltage to current?
Ohm's law.
Yeah, Ohm's law. So delta V, which could also be called swirly E, is equal to IR. So if you want to write this as a current, right, if you want to figure out the current induced, you say current is equal to, right, this would be like this. So you just divide everything by R. So this is epsilon over R, which is equal to negative 1 over R magnetic flux over time. Okay? So your induced current comes from the change in your magnetic flux, and the negative sign indicates that it opposes the change. But if you want to do it mathematically, you can do it this way and then use Lenz's law to figure out which way the current's going. I mean, this is the formal definition, but as always, don't be confused by mathematical negative signs. Draw the picture, do the whole thing. Okay? So yeah, this is the current is then determined by Lenz's law, and you can use Ohm's law to get the current from the EMF. Okay? People are like scribbling madly.
Why? How come there's no negative sign on that?
Oh, because it's the absolute value. So we're just looking for the magnitude here. Okay. Yeah, so what I was saying was, you write it like this. This tells you that it opposes the change, but when you're actually doing problems, you want to figure out the numbers this way, but use Lenz's law that we've been practicing over and over to figure out the sign. Because it's not as simple as there's so many things that depend on the orientation and the directionality that this just tells you we know that it opposes the change, but in practical terms, you're going to have to do a little bit more. Okay? So we don't always trust the mathematical negative sign. We want to find the sign from the physics. All right. So let's try out an example and actually apply Faraday's law using numbers. Okay, so we have a loop of wire. It's got a 6 centimeter diameter. That's just that circle. All right. And it has a resistance of 0.01 ohms. So we say there's a magnetic field shown, and which way does the magnetic field point? Into the page. Okay, it's decreasing linearly from 1 Tesla to 0.4 Tesla in 1.2 seconds. All right, we want to know what are the magnitude and direction of the current induced. Okay, so we're gonna start with this. So let's draw our loop. All right, this thing has a radius of 3 centimeters.
Oh yeah,
Radius is
Radius of 3 centimeters of a magnetic field going into the page. So what's happening to this magnetic field? Decreasing. Okay. So we start with this. So we have this negative, well, it's just d phi m over dt, and we have our current is equal to that over r. Alright? What do we know about flux?
A dot.
Yeah, and what do we know about A and B here? So,
Dot product, something like that.
what do we know about B?
B is
In the page.
Page. Okay?
Okay.
It's not constant in time, but what do we care about here? So when we did flux, when we calculated the flux, did we worry about time?
No.
No. Okay, what did we worry about?
Area.
Area, right? So we're worried about space. So is your magnetic field changing along X or Y?
No.
No, right? It's uniform in space. It's uniformly getting smaller over time. Okay? And the other thing is this magnetic field parallel or perpendicular to the area vector?
Perpendicular.
To the area vector.
Oh, parallel.
Parallel, which means the dot product goes away. So we just end up with BA. Alright? Now, which of these is changing in time? B. Okay? So this becomes, so we have d dt of phi. In this case, phi is B times A. Which one of these things is constant?
A.
A. So we can pull A out. Then we have dB dt. Okay? What does it mean when we know this decreases linearly
at a constant rate.
at a constant rate? So what happens to our derivative?
Just becomes a coefficient change.
It becomes a change. We can call it delta B over delta T. Okay? What is delta B? What's the change in the magnetic field?
0.6.
0.6, because it's 1 Tesla minus 0.4 Tesla. Or is it? Yeah, but
Yeah,
the
the-
sign. So this is remember, this is all absolute value because we are finding the sign from Lenz's law. Okay? And actually, well, we'll get there in a minute. But let's move this over here. So we get A delta B over delta T. So what's A?
R?
What's the area of what?
The ring.
Circle. What's the area of a circle?
R squared.
Pi r squared. Okay? This is going to be pi r squared, and then we have delta B over delta T. Alright, so this is pi times 0.03 meters squared. Delta B, that's going to be 0.4 minus 1, so negative 0.6, but we're taking the absolute value. We'll just call that 0.6 Tesla. And then this is divided by 1.2 seconds. Okay? So once again, absolute value, absolute, this is negative, but we don't care. And so we plug all these numbers in, and we get an E or whatever of 1.4 times 10 to the negative 3. What are the units on that? Yeah, that is volts. Okay? So that's our EMF, but what are we looking for?
Current.
Current. So in order to get current, we take our EMF and we divide it by R. So that's 1.4 times 10 to the negative 3 volts, or 1.4 millivolts, divided by 0.01 ohms, and that gives us 0.14 amps. She can also write as 140 milliamps. Okay. Any questions?
Direction?
What about the direction?
Clockwise. Good question.
Clockwise. Why?
Right-hand rule.
Yes. So what's happening with this magnetic field?
Decrease.
Decreasing. Okay, so that means your induced field should be in the same direction into the page. That gives you a clockwise current. Okay, so this is your current. All right, so when you're doing these Faraday's law problems, you want to figure out the flux. Okay, then you figure out how the flux is changing with time, and that should give you your voltage. If you want the current, you just divide by your resistance. All right, so always start with the flux. And remember, the flux is actually fairly complicated because the formal way of writing flux is B dot dA. So you have to figure out the orientation of the magnetic field area. You have to decide which one of them is changing. And this asks if it's changing in space. This asks if it's changing with time. You guys want to try one on your own? It's a rhetorical question. Okay, so we're showing this loop being pushed into a 0.2 Tesla magnetic field at 50 meters per second. So it starts down here and it's getting pushed into this field. And you can see this field has a distinct boundary. So it stops right here. So not all of the loop is in the field at any one given time. So let's look through this. We know this is the magnetic field. Okay, so 0.2 Tesla. 0.2 Tesla magnetic field. Magnetic field's not changing per se. It's a constant magnetic field. But there is something changing because we have movement. So here's this. Oops. This is our 50 meter per second speed. So that would be this. Because we know this ring is moving. And we also know that the resistance of the loop is 0.5 ohms. We want to know the direction and magnitude of the current in the loop. So we're going to need to use both Faraday's law and Lenz's law in order to figure this out. And so we're going to want to start from Faraday's law. So remember, Faraday and Lenz both sort of come from the same equation. So that's going to be E is equal to negative d magnetic flux dt. Now, Lenz's law takes care of the negative sign, and then Faraday is going to be this other thing. So let's do the magnitude first. All right, so we're going to do d dt of the magnetic flux. But the magnetic flux, remember, is this integral of b dot dA. If we're looking at our particular object that's going into this thing, we can see that B is going to be constant, right? This is our B is 0.2, but our A, in this case, is just this area. Now, why is it just this area? Well, that's because all of this stuff over here
have any magnetic field going through it. So even though we know there's a constant magnetic field, it matters how much of the loop is in this magnetic field region, because down here there's actually no magnetic field. So the only area of the loop we care about is the area that contains magnetic field, okay? Because really this is an integral, so we're taking at each point the area times the magnetic field. So if you get all the way down here, you're doing area times 0 and it doesn't count, okay? So effectively that brings us to B, right? This is just going to be B because that's constant, times the area. Well, the area, this is a rectangular thing, so you can say this is your Y, but of course we aren't even given this length, and we only care about the area that's inside the field, and then this is our X, which we're given to be 5 centimeters. Okay, but I'm just going to write that this way, so this becomes BXY, but remember Y changes with time. Alright, so we're going to plug that in here, BXY, and so when we look at our derivatives, dB dt just doesn't do anything, so B can come out, X can come out because this length doesn't change with time, but we can still take a time derivative of Y. And because we can take the time derivative of Y, this should start to look like something familiar. dy dt, if you think back to Physics 190 and kinematics or whatever mechanics class you took, dy dt should look very, very familiar. Because remember, if you take a time derivative of position, you end up with velocity. So this is the velocity in the y direction. Now, fun fact, we know what the velocity is in the y direction because it's 50 meters per second. So now we have all of these values. We can plug in numbers. So this is 0.2 Tesla. See, I told you that was constant. We can just plug it in. This is 5 centimeters. And then this is 50 meters per second. So our actual voltage is going to be about a half a volt, 0.5 volts, okay? And if we want the current, well, then we just have to go back to Ohm's law. So that's just going to be V equals IR. So this is going to be V over R, which is 0.5 volts divided by 0.5 ohms. And conveniently, this just gives us 1 amp. So we're looking for current. We want magnitude. That's our magnitude. But we still need direction. Okay? And to get direction, now we have to go back to this Lenz's law idea. And the direction is going to come from the fact that if you look at this thing as it moves, right, the area gets bigger as it goes into the field. So that means your magnetic flux should be getting bigger. Okay, so you have an increasing magnetic flux. If you have an increasing flux, that means your induced field, your induced magnetic field is going to oppose the change, which means whatever induced magnetic field you get in here is going to be into the page. Well, because of that, you point your thumb into the page, and now you know that your current should be going clockwise. Now, I just want to point out that there's going to be some interesting phases. So if you want to just think about this thing before it gets in here, before it comes into the field, it's going to have a magnetic flux of 0 because there's no magnetic field. As it enters, it'll start to have a magnetic flux. If it goes all the way into the field, then if it stays in a constant field and it's completely immersed in it, then it will once again be 0 current. So there's going to be some transitional phases. I want you to start thinking about that. Anybody seen this
flashlight
Yes.
on TV. Okay? So, how does this flashlight work, even if without batteries? You shake it.
Oh,
It's
Jesus.
the worst
Which is-
flashlight ever.
It's like a shake weight. If there's an emergency,
Exactly what
you'll
it
look
is.
stupid, but you'll be safer. Okay?
Well,
So-
that's too dark to see.
I mean, everybody owns a phone, so.
It's actually nice if they have a battery too, so you can shake for a while and then stop shaking and rest. But so how does this actually work though?
Yeah.
What's inside this flashlight?
Coil.
A coil of what?
Wire.
Wire. Yeah, you have a coil of wire attached to a light bulb, and then what are you shaking?
This is a for real product.
What?
This is a for real product.
Yeah.
Yes.
You've never seen it?
If you want, I'll bring you one
Well,
and you
man,
can
yeah,
demonstrate for us how it works. So we have a little magnet that slides around inside, and when you shake it, what are you doing? You're changing the magnetic flux by moving the magnet through the coil, which generates a current in the coil, which turns on the light. Because once you have current flowing through your little light bulb, now you have light. Okay? And you probably want this to be an LED so you don't shake quite so hard to get it going, but it's going to have to be a bi-directional LED. You guys know, how many of you guys know what a diode is? Some of you. So diodes, the main difference between incandescent bulbs and LEDs in terms of what we care about for household use is that the current can only go one direction through an LED. So pretty much all your LEDs are set up so that they're bi-directional. Usually that means it's like designed to basically be two LEDs, one with each. The current goes one way, it turns on that one. The current goes the other way, it turns on that one. Remember when we did the lab with that bi-directional LED, we picked them so one was red and one was blue, and you could tell which way the current was going. An incandescent bulb, one that just has a filament that glows, doesn't care which direction your current is going, so it's a lot easier to make. They're a lot simpler, but they use a lot more energy because they heat up. Okay, and an LED doesn't really get hot, doesn't waste a lot of energy, turns almost all the energy into light, which is your goal, unless you're using it for an easy bake oven, in which case you want heat, so you can slowly bake a crappy cake. Okay.
So how much do you have to shake this thing for it to be useful? Like,
Quite a bit.
Assume.
Couple minutes.
That's what I'm saying,
Yeah,
like,
you shake it for a couple minutes and it's on for a few minutes, and then you shake it for a couple minutes and it's on for a few minutes, and it's also just really good for your core strength. Just like engage your core while shaking it. Get two of them so you don't get lopsided. Anyway, so sliding the magnet back and forth between the coils changes the magnetic flux, generates a current, turns on the light. Okay? Alright.
exciting electrons.
Yes,
Right?
they're very excited. Okay.
Oh,
You're gonna get the electrons all
I
excited.
thought
so
that
they
was
like
totally
light.
something
This
different.
is a good joke.
Just like, why is she putting that up there?
No, it's pretty. Okay, please discuss what again. Okay, so original magnetic field points which way?
Into the page.
Into the page. Okay, is the flux increasing or decreasing?
Decrease.
Decreasing. Look, this field stays the same, but the effective area is getting smaller as the loop moves out of the field. Okay, so because we have a decreasing flux, our induced magnetic field points in the same direction as the original magnetic field, which means we have a clockwise current. Okay, so we're getting better at this. All right.
Hesitant to say that. It sounded hesitant to
No,
say that.
it's getting better.